Good morning, my listeners and viewers from wherever you are. Welcome to this lesson, Elimu Live on KUTV. I'm teacher Donald Ndombi from M-Pesa Foundation Academy. And this morning I want us to discuss on cathode rays. So I expect you as a learner who takes physics, by now you know that physics is divided into three: paper 1, paper 2, and paper 3. Paper 1, heat and mechanics; paper 2, electricity and magnetism; and paper 3 is the practical paper. So I want to make you aware that cathode rays is one of the key topics in paper 2, and it's a form 4 topic. So if as a learner, every time that your teacher introduces a topic, you should be able to know whether that is a paper 1 or a paper 2 topic. So cathode rays is a paper 2 topic. In form 4, we have 11 major topics. Only 2 of them are in paper 1 and the rest are in paper 2. I look at them as modern physics. Therefore, under cathode rays, by the end of this lesson, I expect that you'll be able to do the following. 1, define key terms. So our main objective for these lessons, 1, by the end of this, you should be able to define key terms associated with the cathode rays. Number 2, you should explain the production of cathode rays in the cathode ray tube, also called CRT. You should be able to give us the properties of cathode rays. You should be able to explain the main parts of the cathode ray oscilloscope, what we usually call the CRO. This one is examinable, and you should be able to handle at least 1 or 2 questions that come in KCSE. Now, I have a question. If I take you back to Form 2 chemistry, the structure of the atom, on the periphery of any atom, on the outermost energy levels, we have what we call electrons. So this tells us that on the surface of any metal, we have what we call electrons, which are free to move. Now, I want to ask a question. What happens when a metal surface is heated? When you heat this metal, what happens? That is my question to you. What do you think? What happens? So if this was my metal and I heat this surface, remember electrons are microscopic elements, microscopic particles. You can't see them with your naked eyes. But if this was a surface of a metal and you heat it, what will happen is the electrons will gain energy and break loose from the nucleus. Slide 3, my producer. Electrons will break loose from the nucleus. They'll gain what we call kinetic energy, so they'll start moving. Now, because of this movement that is caused by heating, we call this process thermo-ionic emission. From 2 words, thermo, you need to remember, thermo means heat, and the other word is from the ion. So they are particles but in ionic form. Therefore, when you hit the surface of a metal, what will happen is the electrons will gain energy and start moving. They break loose. Once they are free, they can move in any direction. Therefore, what do we say? This process is called thermo-ionic emission. This one is testable and it's examinable. You can be told, explain the process by which electrons are emitted from a metal surface. You say by the ionic emission, because it is caused by heating. Okay, how are cathode rays produced? That is our next question. How are cathode rays produced? So we look at production of cathode rays production. How are they produced. If in a paper 2, section 1, this will be about 3 marks. You are expected to explain, and you'll be awarded 3 marks. Production of cathode rays. Slide 4. So cathode rays, what are they first of all? Back a bit. What are cathode rays? Cathode rays are streams of electrons emitted at the cathode and moving towards the anode. They are produced where? At the cathode. And they move towards what? The anode. Back to form 2 still, you need to remember cathode is the negatively charged electrode, is the electrode that is connected to the negative terminal of a source of energy, and the anode is the positive. Now we are hitting this cathode. Once we hit the cathode, which is a metal surface, what happens? Electrons are released. These electrons are negatively charged. They are negatively charged. By the basic law of charges, unlike charges will attract. Therefore, they are attracted towards what? The anode. So they are produced at the cathode, then they start moving towards the anode. They are attracted towards the anode. Therefore, that stream of electrons, they are moving together to form something like a beam. But it's not a beam of light, but a beam of electrons. That's what we are calling what? Cathode rays. Now you need to know, where are they produced? Where do we produce cathode rays? Can we produce cathode rays wherever you are seated right now? Yes or no? We always produce cathode rays in a cathode ray tube. So it's a special tube with a heated cathode and an anode. So they are produced in a cathode ray tube. What happens? Electrons produced at the cathode by the muonic emission are accelerated towards what? A fluorescent screen. So the work of the anode is simply to attract the electrons produced at the cathode. And we are saying they are moving towards a fluorescent screen. There is a screen this side. What is the screen for? As I mentioned earlier, electrons are things we cannot see with our naked eyes. We can only realize their presence if they hit a fluorescent screen and it will glow. So to help us, these electrons that were produced at the cathode, to reach the screen, there is the anode, which is positive, and will attract these electrons to start moving in that direction. Then once they hit the screen, it will glow, and that will help us actually realize that we have what? A stream of electrons that was moving. Now look at this diagram. Look at the diagram in our next slide. So that is the cathode that is being heated. You can see those small dots. Those are the electrons. When that cathode is heated, they get excited. They gain that electrical energy, and it's converted into kinetic energy. Then once someone gains kinetic energy, you'll start moving. So they start moving. The next slide shows you that they start moving towards the screen. So there is an anode there which is attracting these electrons to move towards what? Towards the screen. So in our next slide, you see the electrons are now moving. You can see the blue dots. Those are electrons moving, and they have been produced by what? The ionic emission. You can see them moving, a stream of electrons. And the next slide shows you they can even form a beam, like light, like the way light comes from a torch. You can see that's a beam of electrons. They are moving towards what? Towards the screen. But what enables them to move like that? It is the anode, which is positive, that attracts them towards that screen. Now what happens? In a simple diagram, the next slide, you will see we can represent the whole of this process using a simple diagram of a cathode ray tube. On your far left, there is the filament. What happens to this filament? it is a heated wire from which electrons are emitted. And you can see from the filament, the next we have the anodes. The anodes are positive. Therefore, what will they do? They'll attract those electrons that were produced at the cathode to start moving. So they'll keep moving like that in a straight line to form a beam of electrons. Then you can see a screen on the far right. That green dot there shows you that that screen is a fluorescent screen. So it is made of a material that when electrons hit it or have an impact on it, it will glow. Therefore, you can see that on the far right, that green thing, that green dot, shows that electrons have hit the screen at that particular point. So that screen, we are not talking about a mirror, we are not talking about any other screen, but we are talking about a fluorescent screen. So this simple diagram shows you that from the cathode, electrons are produced by what? The ionic emission. Then they are accelerated towards the anode by those anodes towards the screen. Once they interact or impact on the screen, it will glow, and you will see that green thing. So this is what actually happens, and you will see towards the end of this where we apply this. Do you know how even you see an image on the television screen? Do you know how even you see when you take a photo or using your camera, your phone, and you see the image on the screen? Do you know the process that happens? Those are some of the applications of this, as we shall see at the end of this. Now, in the next slide, we have now the cathode ray tube. Now, you are supposed to familiarize yourself with this diagram. Someone can ask you, using a well-labeled diagram of a cathode ray tube, explain the production of what? Of cathode rays. Remember, we said cathode rays are produced in the cathode ray tube. And in our previous slide, we have seen a simple diagram, just a filament here. We have seen just a filament, then we have seen anodes, then we have seen a screen. Just to help us understand that we produce electrons at the cathode or the heated filament, then we have the anode which attracts them towards the screen. Once they hit the screen, it glows. That is a simple diagram, but now we want to look at the real cathode ray tube. How does it look? What are the main parts? Now in our next slide, that you can see the main parts of a cathode ray tube. One is the cathode on our far left. Then you can see from the cathode, which is connected to the negative terminal of a power source. We call it extra high tension power. That is a power source of a high voltage, so that the heat produced, it can cause enough production of the cathodes. Now we will not use just any material at the cathode. We need a material which will produce electrons at the smallest possible energy. Later on in topic 9, we shall call that a material of low work function. So we have talked about work function. Later on we will look at that. So the material used as the cathode must be a metal of low work function. What is work function? Work function is simply the energy required for a material to produce what? Electrons when heated. So if we use a metal of high work function, it means we will require a lot of energy for us to produce a stream of what? A stream of electrons. Therefore, we require a metal that will produce electrons at the smallest possible or at the least energy. Therefore, I'll ask you, can you think about metals that we can use as the cathode? Think about that. Then from the cathode, we go to the anodes. You can see the anode in that slide. You can see the anode which is connected to the positive terminal of our power source. That means the anodes, these are electrodes. There are still other metals, but they are connected to the positive terminal, so they are positively charged. They have only one function. Once the electrons are produced at the cathode, they attract those electrons. So we shall see electrons moving, and they move as a stream towards the screen. Then you can see on the far right a fluorescent screen. Now that tells us that we cannot use any material to make the screen. It must be a material that will glow. That's why we are calling it a fluorescent screen. So some of the materials that we need here that will glow is, for example, barium sulfide. So materials that we use on the screen will include barium sulfide. This, when on interaction with the electrons, it will glow, which will produce the green dot that we saw in our simple diagram. Now I have one question. If you look at from the heater to the anode to the screen, in between there is a vacuum. You can see a vacuum. Why do you think that is a vacuum? What do you understand by a vacuum? It is a place with no matter. There's no matter. You know, there's three states of matter. There's no solid, no liquid, no gas exists in a vacuum. Why do we need a vacuum in the cathode ray tube? Look at where the cathode rays are coming from. The electrons are produced to the far left at the heater there on the cathode. Then they need to move all the way to what? To the fluorescent screen for us to realize that they are present. Therefore, if this was done in an open air, like where I am right now, what will happen? If they're coming from this end to this end, they'll meet some air particles here in between, which will stop them from reaching the screen. Therefore, someone watching at the screen will say there are no rays, there are no electrons, there are no cathode rays. Why? They'll interact with what? Air particles. So we evacuate the tube. Evacuate means we make it a vacuum so that we minimize or we eliminate the interaction of the cathode rays with matter. In this case, air particles. That is a point you need to note. It is examinable in paper 2. They'll ask you, why do we evacuate the cathode ray tube? And we have said our simple answer is to eliminate or minimize interaction between the cathode rays as they move from the cathode towards the screen with air particles. Okay. Now, most of us will summarize this process in different ways. We can use a flowchart to explain the same thing. Look at this flowchart here. We can use a flowchart or use the other diagram to explain the same thing. So if you are asked, explain the production of or the working of a cathode ray tube, you just use this flowchart. 1, the hot metal filament emits electrons. Remember? Once the electrons are emitted, what happens? The electrons are attracted to the anode and accelerated. Accelerated simply means their speed is increased. So they are accelerated so that they continue moving. Then what happens as they continue moving? The electrons will strike the fluorescent screen, and the beam is seen as what? A spot of light. It will be seen as a spot of light. This is a simple diagram. So in your own way, find a way of memorizing this or explaining. Do not cram. Don't cram the diagram. Don't cram the flowchart. Don't cram the wording. What is important, you tell us how the electrons are produced and where. Tell us how they move and what helps them to move. And tell us how we can notice that we have been having a stream of electrons. If you are able to do that, whether you will use a flowchart, whether you will use a simple diagram, you will make sense to the person looking at your work. So it's up to you. Choose one. We have several ways of presenting information, so it's up to you as a learner to tell us when we ask you, how does a cathode ray tube work? It's up to you. I can also change the question and ask you, explain the production of cathode rays in the cathode ray tube. It's up to you to choose one of those and do what? And explain. Now, we have just looked at the production of cathode rays. The next thing we need to discuss is their properties. Properties of cathode rays. Cathode rays. What are their properties? Properties of cathode rays. There are quite a number. We will look at the main ones and just mention others. Property number 1 of cathode rays. The way we have seen, they always travel in a straight line. Cathode rays travel in a straight line. What else do you know that travels in a straight line? Yeah, you can tell your young brother or your young sister. What else do you know that travels in a straight line? I can see some guess. Light. Yes, light travels in a straight line. In Form 1, you looked at rectilinear propagation of light. Rectilinear propagation of light. And when you are handling light in Form 1, you are looking at shadow formation. Shadow formation. If your sibling in grade 2 asked you, how do we form a shadow? What will you say? How do we form a shadow? What will you say? If you will actually say, if I take an opaque object in front of light, then a shadow is formed. Why do we form a shadow? Like if this is a source of light, let's say this is a source of light. What do you think is this? This is the sun, correct? This is the sun. And you have some opaque object here, like this. What will happen? As light comes, light travels in a straight line. On reaching this opaque object, opaque actually means light cannot pass through. What will happen? These light rays are stopped. And one property of light, it cannot bend. Light will not behave like some of you. If you realize this route was blocked, then you go the other way. You go like this. Light will not do this. So what will happen? When this beam of light is stopped here, a shadow is formed. So we shall see a dark thing on the other side. Just with the same shape like that. And this is what we are calling what? A shadow. This is a shadow. So one way of testing that light travels in a straight line is formation of a shadow. Now, in a similar way, if we go back to our cathode ray tube, then we place an opaque object in the path of cathode rays, as you can see on that diagram. What do you see on the far right? A shadow on the screen. That means the cathode rays did not even reach the screen. They were blocked by that opaque object. Therefore, the formation of a shadow in the path or on the screen when an opaque object is placed in the path of cathode rays is a clear indication that cathode rays travel in a straight line. What is the other property? Property number 2. Cathode rays are particulate in nature. So note down the key properties. We have said 1, they travel in a straight line. Travel in a straight line. Then number 2, we are saying they are particulate in nature. Particulate in nature. In other words, these are just particles. They are particles. Cathode rays are particles. And what are some of the properties of particles? In Form 2 again, you looked at the structure of the atom, and you could talk about the atom either being neutral. Neutral means no charge. Or it could be positively charged, or it could be negatively charged. So any particle will either have no charge, what we say neutral. It will either be positively charged or negatively charged. Therefore, cathode rays possess one of these properties. And we cannot say they are neutral or positive or negative until we test them. And the first test, how do you know something has a charge? You take it through an electric field. So look at part 1. The way you can prove that cathode rays are particulate in nature is 1, you take them through an electric field. Look at that diagram. The next slide shows us here. You can see we have a deflection of the beam in an electric field. The previous one, the previous slide. You can see as the electrons pass through an electric field, they are deflected. Where to where? You can see in the electric field, the upper part is positive and the lower side is negative. So that straight line, they were moving between K and A in a straight line. After passing through the electric field, look at where they go, upwards. What does that tell you? If they are moving towards the positive, that means they were attracted there, so they are negative. So we can easily say cathode rays are negatively charged, as seen by what? When we take them through an electric field. Is that clear? So if you are not able to explain the same thing, you can simply tell us. If you forget this particulate in nature, be simple, just say they are negatively charged. Negatively charged. This is a property of what? Any particle. So cathode rays are negatively charged. So when they pass through an electric field, they are deflected towards the positive. Now, still on particulate nature, we also want to take them through a magnetic field. We want to take them through a magnetic field. And look at the next slide. If we take them through a magnetic field, how are they deflected? If you look at that slide, what do the crosses mean? If I may take you back to Form 2, magnetic effect of electric current in Form 2. So in a magnetic field, you can see if we take cathode rays through a magnetic field, we can predict whatever will happen to them using Fleming's left-hand rule. Now I take away the first one, go back and revise and state Fleming's left-hand rule. So if you hold a conductor in your left hand like this, this is my conductor, I'm holding it in my left hand, such that the thumb is pointing in the direction of motion. The fingers will always point in the direction of field. So you can see, this is my left hand, the thumb is pointing in the direction of motion, as you have seen. So the cathode rays are moving in that direction. So the field is always in the direction of the fingers. That means the cathode rays are deflected towards that direction. So they are deflected in a magnetic field. Is that clear? So we have said particulate nature of cathode rays. 1, they are deflected in an electric field. In which direction? Towards the positive. Why? They are negatively charged. Then in a magnetic field, they are also deflected, and we can predict the direction using Fleming's left-hand rule. Now, other properties that you may mention, something good is those 2 that we have mentioned, or the 3, rectilinear propagation, or they travel in a straight line. We have also mentioned particulate nature. Those, we can test you on that using diagrams. So you should be able to tell from a diagram why, or explain using a diagram how you can tell us the properties of cathode rays. Other properties will include they produce fluorescence. So we have talked about straight line, that is number 1, number 2. Then number 3, they cause fluorescence. They cause fluorescence. What does that mean? they'll make, when they interact with some materials, they will glow. As we saw the screen, they will glow. Then number 4, cathode rays, when stopped, they produce X-rays. They produce X-rays. Now I may explain this a bit, though you will look at X-rays as a topic on its own. The basic way of producing X-rays is simply putting an obstacle, a metal of a strong or a metal of high work function in the path of electrons. So if these were electrons, for example, and there is a metal here, this is a metal, and these were electrons like this, what will happen is they cannot penetrate. So they don't have enough energy to penetrate through this metal, depending on the type of metal. For example, lead, they cannot penetrate through. So what will happen? They are blocked, and they'll come this other side like this. They are blocked, so they'll turn. So depending on their energy, these ones forms what we are calling X-rays. X-rays. Don't ask me what happens when someone is taking X-ray in a hospital. You are not a metal, so these electrons will penetrate through you. That's why you are placed in a special machine. There's a special place. If this is your place and you put your hand like this, wherever you place your hand, that is the metal we are talking about. That will stop what? X-rays. And when they come this other side, they'll now show us the picture of the fracture that you have. So that is how X-rays are produced. So when we stop cathode rays with enough energy, they can produce what? X-rays. That is another property. So they possess energy. Which energy do they possess? Any guess? They are moving. Which energy do they possess? Kinetic energy. They possess kinetic energy. So the kinetic energy can be changed into another form and to give us X-rays. So that tells us one important application of cathode rays, that they are used in production of what? X-rays. We cannot talk about X-rays without electrons. We cannot. There must be some heating, then electrons produced, then the electrons stopped by a metal target to produce what? X-rays. Then, and we have already said the last one, they possess kinetic energy. Fine. They possess kinetic energy. That means later on, as we shall be looking at the functions of the cathode ray oscilloscope, we shall calculate energy of cathode rays. They possess, or they have, kinetic energy. If I take you back to Form 3, there's a topic called work energy, power and machines. And you know, kinetic energy is given by what? A half mv squared, where m is what? Mass. And v is velocity. So cathode rays, they possess kinetic energy, one, because they have velocity. They are electrons in motion, and they move with roughly the speed of light in a vacuum. So the speed of light in a vacuum is about 3.0 times 10 power 8 meters per second. So they move with this speed. That is a super high speed. And they have mass. I send you back to Form to find the mass of an electron. So an electron is, they are particulate in nature, and matter has mass and occupies space. Therefore, we can calculate the kinetic energy using this. In an exam situation, on the cover page of your paper, you are always given these constants. Mass of an electron equals to this. You are supposed to know. So don't ask the teacher, maybe this question has a problem. That is question 18 in most cases, 18, 17, somewhere there. The mass is always given on the top of the paper. So we can calculate the kinetic energy of what? Cathode rays. What did we say were the properties? Property number 1, they travel in a straight line. Number 2, particulate in nature. Number 3, produce fluorescence in some materials. Then they can produce X-rays. And lastly, they possess kinetic energy. Now, Let me ask you a simple question. Do we need electrons anywhere? Do we need electrons? This beam of electrons, where do we use them? So you realize there are so many, but as far as Form 4 modern physics is concerned, you will only look at a few cases. Where do we use the beam of electrons? Where do we use them? Where are used? Someone may ask you, where do we use the beam of electrons, what we are calling cathode rays? And our next slide, you will see we can use them in so many appliances, but the ones that are circled, those are the ones that we will look at later on. Oscilloscopes, television tubes. And when we talk about television tubes, you remember the television tubes which used to look like this. Nowadays we have TFT, but we used to have televisions which look like this. I know some of us at home, look at your television. How does it look? Does it look like this? It used to be called CRT TV, CRT, cathode ray tube. We used to have this as the TVs, but nowadays we have the slim ones. So later on, we are looking at revising the syllabus and now teaching the slim ones rather than this one. Because though these ones are still used in other places. So oscilloscopes, TV tubes, X-ray production, then monitors. And we can also use them in electroplating and combustion engines. So if you are asked where do we use cathode rays, you can mention those few appliances. Now next, I want us to look at the cathode ray oscilloscope, commonly known as CRO. And the cathode ray oscilloscope, I will be referring to it as a CRO, cathode ray oscilloscope. Now what do we need to know about the cathode ray oscilloscope? We'll just look at the main parts. Then we shall look at the functions later, or you can do it on your own. The main parts of the cathode ray oscilloscope. So the first part is called the electron gun. Now when you hear of a gun, what comes to your mind? Gun. What comes to your mind? Don't look around your neighbor, he doesn't have one. When you hear of a gun, what comes to your mind? There is something coming out of it. The usual gun, what comes out of it? Bullets. In this case, our bullets, what are they? Electrons. So the electron gun, its work is just to produce electrons, ensure they have moved all the way to the screen. The electron gun. Another one is a deflection system. Then we have an evacuated strong glass envelope, simply a vacuum, and a fluorescent screen. Now we may test you on each of these parts separately. So we have talked about the main parts. Main parts being one, electron gun. Then we have talked about another one being a deflection system. We have also talked about a vacuum and a screen. These are the four main parts of a CRO. You can simply tell us electron gun, deflection system, a vacuum, and a screen. Now we wish to look at the main parts of each of those parts and how they work. What is their function? So before that, we can also ask you to draw a well-labeled diagram of a cathode ray oscilloscope. How does it look? In our next slide, you see the whole part of the integration of all these parts. You can see them there. One, the cathode and the grid and the anode. All those form what we are calling the electron gun. Why? We produce at that cathode, you can see there, we produce what? Electrons. Then they start moving towards the screen. So what helps the movement? The anode. So they are accelerated by the anode. So we produce them at the cathode, then they move. So that combination of the cathode and the anode forms what we are calling the electron gun. And between them is what we are calling what? The grid. The grid only helps us in focusing the beam. Because we can produce these electrons and they start moving up and down. So you have a grid to lead them so that they are moving in a particular direction and to hit a particular point. So that part of cathode, grid, and anode make up what we are calling what? What we are calling the electron gun. Then, okay, 5 to go. When you move on, you have what we are calling the deflection system. You can see some plates there which look like pedals of a bicycle. You can see them where there is the input and those two pedals there. Those are called the vertical deflection system or the Y plates. Then after the Y plates, on the other side we have the X plates or horizontal deflection system, then the screen. Now if we look at the electron gun quickly, what does it consist of? We have already mentioned in our next slide. You can see it is made up of the electron gun. It's made up of the heated cathode, a grid, and the anode. It's made up of heated cathode. What is its work? To supply electrons. Then the anode, which accelerates and focuses the beam on the screen. Then the grid, which controls the rate of flow of electrons. So the grid will control the rate of flow of electrons. So if you are asked the electron gun, what is its function and the composition? You talk about the cathode, the anode, and the grid, and the function of each. That constitutes what we are calling the electron gun. Then the deflection system, we have two of them. Maybe I can explain something. We have two of them, the deflection system. So one, we have what we call the X plates. Then we have what we call the Y plates. X and Y, this is vertical, X is horizontal. So the X plates or the horizontal deflection, they will always deflect the beam horizontally based on polarities. Now, if you look at the next slide, you will see that the next one, I started with the X. The horizontal plates, you will see, yes. So the stream of electron is coming from left. Then those two plates in between them, those are what we are calling the horizontal plates. Now, if you can see the switch on that, you can see a switch on that circuit there. If it is open the way it is, there is no deflection. So the electrons will hit point O. Now, if you close that switch, if you close that switch, what will happen is you realize that N will be more negative compared to M because it is connected to the negative terminal. Therefore, the electrons will be deflected towards M because M is more positive. Now, because we are talking about an AC input, alternating current, in one cycle, M is positive, so the electrons are deflected towards M. In the next cycle, the M is now negative, so they are deflected towards N. Now, because this happens at a higher frequency, what will happen is continuously. So we have seen our M and N here. Let's say M and N. So it is either deflected towards M or towards N. So continuously, our eye perceives this on the screen of a CRO as a straight line, which is horizontal like that. That's what we are calling X plates. So the same thing happens to the Y plates. Now for the Y plates, which is the previous slide, you realize in one time there is, let's say there is A, C, and B. So when the electrons come like this, when the circuit is open, there is no deflection because the two plates Y1 and Y2 are at the same potential. So there is none of them is positive, none of them is negative. So no deflection. It hits at that point, which is A on whatever you're seeing. Then when you close the circuit, what happens? When you close the circuit, Y1 becomes more positive, so attracts all electrons. So they are deflected upwards to B, then in the next cycle towards C. So this happens at a higher frequency till at the end you will see a vertical line on the screen. That is what we call the deflection system. Now if we talk about the screen shortly, the screen, one, it is coated with what? A fluorescent substance such as zinc sulfide, which glows on impact with electrons. So that the work of the screen is simply to show us that something has happened. So the stream of electrons has hit the screen, so it will glow like that. Then the inside of that tube, it's coated with graphite. Why graphite? Because it conducts electrons to earth. There is what we call earthing. So we use graphite because it conducts excess electrons to earth. Then also that graphite will shield the beam from external electric field, because we need them to move in a particular way. So if we have external electric fields, then that means we shall have interference in the motion. So it will shield, then it will accelerate electrons as it is at the same anode potential. Now take away. Can you try the following model questions? You can take a picture on your screen, or you can note them down very fast, then try them at home. These are KCSE model questions. Number 1, state one way of producing a beam of electrons and define the phenomena. Number 2, what are cathode rays? Give 3 properties of these rays. Why do you think the cathode ray oscilloscope is evacuated? Then name one metal oxide that can be used as a cathode and give a reason. You can do that as a takeaway. And if we shall have time in our next lesson, we will talk about the last slide. We shall talk about the uses of the cathode ray oscilloscope. We have just looked at its main parts. We shall look at the uses, and they are, to mention a few, as a voltmeter, the TV tube, and determining frequency of an AC signal. So you can read on this on your own, especially determining frequency, and that will be great. I am looking forward to having more and more. Remember, I'm teacher Donald Ndombi from M-Pesa Foundation, and we'll be interacting more and more as time goes. Thank you for listening, and have a good time. Stay safe, sanitize, keep distance. Okay, fine.